All right, so for station one, I've got a tank filled with water. And on the bottom of the tank and also along the side of the tank, I've got graph paper so that you can see lines. And the reason that we're going to do that is I'm going to be shining a laser inside the graph paper or inside the fish tank. And I want you to be able to see that the laser is traveling along a straight line. So for the first one, I've got the laser over here. And what's going to happen is it's going to follow this line right here. All right. So as it goes along, you'll see that it's following that line. And as it goes into the tank, you see, it doesn't follow that line anymore. It refracts because the laser goes from one material, one media, in other words, the air, into plastic and water, and they have a different refraction. So you're getting a bent angle. Let me see if I can get this down. See, unfortunately, you can't see. All right, and you also see some of the laser light is being reflected off of the angle, and some of it's being refracted inside the tank. All right, one really cool thing that we discovered is if I shine this in here and I angle it there, to see how it's internally reflecting. So you're getting a little bit of internal reflection off of the left panel and a little bit off the right panel. There it is too. So it's bouncing off of the panel closest to me, and the angle of incidence, the angle of the beam coming in, is equal to the angle of reflection. So you're getting equal and opposite bounce. You can even see that on the graph paper. There's equal area under each of the curves, as your math teacher would say. Looking at it from this angle, if I shine it in, watch what happens when I go to the surface. See, it's reflecting off of the surface. And I've even been able to get it to where it reflects off the surface. There. So it's reflecting off the surface, and then off that wall, and then off that wall, and then going into the back. So I'm getting 4 points of reflection. And if you look over here, you'll see that. It's going up, bouncing off the surface, coming down, hitting the wall right there where it's bright, going back over there, hitting that wall, and then in the back going against there. So 1, 2, 3, 4, 5 points of refraction. All right, of internal reflection. Sorry, internal reflection. That's what that phenomenon is. That's the surface of the water right there. See, there's the edge of the water right there. So that's the surface of the water, and if you angle the laser just right, it is reflecting off the inside. So don't forget, as the light passes from one media, in this case air, into another media, in this case water, it looks like it's bending, and in fact it is bending. It is refracting. All right, so here it is coming in straight, hitting that, angling maybe 20 or 30 degrees, and then going up. So if you look, see, it's going in right on that line, and it's coming out right on that line, but then it angles up, and it goes up. Let's see, rise over run in this case is, it goes up 2 blocks, and it's over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 blocks. So rise over run. It runs 12 blocks and it rises 2 blocks. So those of you that are in algebra and geometry, you can use rise over run to figure out the slope of that line. It should be a straight line, but because of refraction, it is not. Refraction is different than reflection. Reflection is bouncing off of a surface. Refraction is bending as a result of moving from one media, in this case air, into another media, water. So then for the last one, I've got a white light here, and this is a diffracting gradient. Whoops, it's upside down. This is a diffraction gradient, and what this does is it takes that white light and it splits it into the colors of a rainbow. So for the question number, I believe it's 3 on your paper, it says to draw the colors in as they appear through the diffracting gradient, you're going to draw in all the colors that are not there except for when you look through the grating. So make sure you color those in and draw those in. All right. Now they appear to be big rectangles because the source of light is a big rectangle. So you can just do bands. You could do red, orange, yellow, green, blue, and then purple or violet or indigo or whatever you want to call it. All right?
Now I want you to make a prediction. In my left hand, I have a standard-sized basketball, and in my right hand, a 5-kilogram medicine ball. If I drop them both at exactly the same time, which one will hit the ground first?
This is a trick one, isn't it?
The heavy will go down first.
Well, yeah, it'll drop faster. They'll both hit the ground at the same time.
Give me a prediction.
I actually would have thought this one would go faster because it's heavier.
Maybe it's that one. Maybe this one, yeah.
So you reckon this will be faster?
I reckon that one will be faster.
So why does that make it go faster?
Because the weight pulls it down quicker.
What are we measuring when we say, oh, it's heavier? What are we feeling?
Gravity?
Gravity.
Go ahead. Yeah, that's... Oh.
Objects being pulled to the Earth, I guess.
Okay, so which of these objects is being more pulled to the Earth?
This one.
That one, the black one.
All right. Well, here's what we're going to do. I want you to hold both of those above your head. Don't worry. Can you get them really high? Can you? Okay, on the count of 3. Ready? 3, 2, 1.
Yeah! Exactly the same.
Oh, they fell at the same time. Exactly the same time.
They hit at the same time.
Was that what you expected to see?
No.
So what do you make of that?
I need to go read more books.
Magic?
Gravity is going to pull at the same rate, no matter how heavy or how light it is.
But gravity is how light or how heavy something is.
It's one big, massive mind. There must be some force that's dragging them down, and actually the actual weight of it doesn't matter.
Something to do with mass or something.
I can't remember why.
It's almost like the weight holds it back in a way, even though that doesn't seem to make sense.
I think you might be hitting on an interesting point there. Weight holds it back. Now, it's not actually weight that holds it back, but inertia. That's the tendency of matter to maintain its state of motion, so to remain at rest if stationary, or to continue with constant velocity when in motion.
What's the big idea?
The big idea is this one has more mass, so it's got more weight, which you can clearly feel, but it's also got more inertia, which means it's also more sluggish.
Right.
It tends to resist acceleration. So that greater force is required to accelerate it at the same rate as this ball.
Like a heavy car trying to accelerate.
Like a heavy car trying to accelerate, you need more force to get it going.
Yeah.
Exactly. So what does all that mean? Well, the force on the medicine ball is greater than the force on the basketball, but it has more inertia. And what's really important is that the ratio of force to inertia is the same for all objects. So everything accelerates at the same rate and lands at the same time.
Here's a physics classic. Suppose you drop a golf ball and a bowling ball from the Empire State Building. Which hits first? Answer? They hit at the same time. It could be a marble and a piano, a banana and an anchor, or any two objects for which air resistance won't be a big factor. The idea is that everything falls at the same rate, no matter what its mass is. A lot of folks have trouble believing this. It just doesn't seem right. Oftentimes we say, but a bowling ball weighs more than a golf ball. Doesn't that mean gravity is pulling on it more? Well, there's a distinction to be made here. The bowling ball has a greater mass, so there's more stuff for gravity to act on. So yeah, in that sense, gravity is pulling on it more, but it still doesn't fall any faster. Why not? To understand why, ask yourself this question. Which one is harder to move? The bowling ball, of course. It takes more force to move the bowling ball, and the bowling ball is also the one gravity pulls on more. A smaller object is easier to move. It also has less stuff for gravity to act on. So why do they fall the same? That's the cool part. These two factors exactly balance each other out. That's why any object, from dump trucks to linguini, fall at exactly the same rate as any other.
This is NASA's Space Power Facility near Cleveland, Ohio, and it is the world's biggest vacuum chamber. It's used to test spacecraft in the conditions of outer space, and it does that by pumping out the 30 tons of air in this chamber until there are about 2 grams left. And it's kind of got an eccentric construction, which is part of its history. It was built in the 1960s as a nuclear test facility to test nuclear propulsion systems. And that meant that they built it out of aluminium to make the radiation easier to deal with. Aluminium is not the best thing, the strongest material to build a vacuum chamber out of. So they built an outer concrete skin, which is part radiation shielding and part an external pressure vessel, so that this thing can take the force that's present on the outside when it's pumped out to the conditions of outer space. Galileo's experiment was simple. He took a heavy object and a light one and dropped them at the same time to see which fell fastest. Now in this case, the feathers fell to the ground at a slower rate than the bowling ball because of air resistance. So in order to see the true nature of gravity, we have to remove the air. It takes 3 hours to pump out the 800,000 cubic feet of air from the chamber.
Okay, we dropped 2 millitorr in the last 30 minutes.
But once it's complete, there's a near perfect vacuum inside.
6104 manual, 10% open. Station 1, go for drop. PCV 30-1, pressure set point at 240 psi. We are go for drop.
10, 9, 8, 7, 6, 5, 4. Cameras on. 2, 1. Release.
Exactly.
Look at that.
They came down exactly the same. Wow.
So these are the colors of the visible spectrum. You've got red, orange, yellow, green, blue, indigo, and violet, which are purpley colors. And as you move through the visible spectrum, you wind up with increasing energy but decreasing wavelength. So at the bottom end of the scale, at the red end of the scale, those have longer wavelengths and they have lower energy. And as you move up, orange has a smaller wavelength and higher energy than red. Yellow has a smaller wavelength and a higher energy than green, than orange, all the way up to violet. Violet and indigo have the highest energy and the smallest wavelength. Now, a prism is a piece of glass or a small object that will take white light from the light fixtures, from the sun, and it'll split it into its component colors. So you get a rainbow out of a prism. You have seen this happen before outside because a water droplet is like a little prism. And when it rains, you get a rainbow like this one here. So if you're standing in the right place with the sun behind you and the rain in front of you, and I believe it's a 33-degree angle, then you can see a rainbow every single time. You can make a rainbow if you get your garden hose out and you stand with the sun behind you and you spray the water in front of you, you can make a generic rainbow. Now, you see colors because objects in your world around you absorb and reflect different amounts of light. In the case of a red object, like this red apple, the sunlight shines on the apple, it's shining on it with red, orange, yellow, green, blue, indigo, and violet. The apple is absorbing orange, yellow, green, blue, and violet. It is reflecting the red. So your eye only sees the color that is bouncing off the apple, reflecting off the apple, and hitting it, so you see the apple is red. In the case of a leaf, the leaf is absorbing red, orange, yellow, blue, indigo, and violet, and it is reflecting the green. So the stuff that is getting absorbed, you do not see, and the colors that are getting reflected, you do see. For transmission, transmission is when light passes through an object. You've seen this if you've looked through a window. If you can easily see what's on the other side of the window, that is a translucent object. The light is coming through unimpeded. You can see all the way through. You can read signs. You can identify people. You can see, animals from afar. You can see somebody's house from way far away. If the glass is not transmitting perfectly, if it's only transmitting a little bit of light, then that's translucent. If you've ever seen a stained glass window, you know that there is light coming through the stained glass window, but if you look through a stained glass window, you can't see objects on the other side because it's not allowing all the light. It's blocking some of the light and allowing some of the light to come through. Reflection is where the light gets bounced off of the object. So in the case of the apple, it's reflecting red. In the case of the leaf, it's reflecting green. In the case of a mirror, it reflects all of the light. So when you look in a mirror, you see everything bouncing back at your eye, so you see a reflection of the things that are behind you or in front of the mirror. So what's happening is, if you saw in the images on the previous section, white light's coming down. White light contains all the colors of the rainbow. It contains red, orange, yellow, green, blue, purple, indigo, and everything in between. And it hits this punching bag. The punching bag absorbs orange, yellow, green, blue, purple, indigo, all of those colors. When the red hits it, it bounces off and it comes towards your eye. When it hits your eye sees that object as red. In reality, the object is absorbing everything but red, so it's every other color. But your eye has been trained to see color based upon what's being reflected back at it. If I turn off the lights and make this room dark and hit with the red flashlight, there is only red coming out of here. Everything in the room will appear red. What color do you think this is going to be? All right, let's find out. So now it's nice and dark. Here's the red flashlight. Looks white. And so does the fire extinguisher over on the wall. They look white because the only light that's coming out of the flashlight is red light. So everything around it is reflecting red light or it's absorbing red light. So if it's absorbing red light, it appears black. If it's reflecting red light, it appears white. Now, something cool that can happen is if I just change the quality of the light that's coming out of here, if I change it from red to green, then watch the image. I'll step back and I'll do this real quick. Look, the punching bag, the fire extinguisher, everything's black now because there is no red light coming out of this flashlight. There is only green light coming out of this flashlight. And because there's only green light coming out of the flashlight, the punching bag appears to be black. The fire extinguisher appears to be black. Everything in the background is either a whitish color because it's reflecting green, or it is black because it is absorbing the green light. All right? If I turn them both on, then I get a little bit of green and a little bit of red, and you see things in their natural color, or close to natural, because there's no blue light coming out of here. If I remove the red, there it is white again, and now black, and white, and black. I could do that all day. Make sure you look at the punching bag and the fire extinguisher on the wall. All right, I'm going to stop because I'm making myself dizzy.